Hi, today I'm going to talk through an example of showing that an algorithm is correct, complete, and finite. And we'll do this with an algorithm that calculates powers of 2. So let's take a look at the algorithm. So the input here is a non-negative integer n, and then the output is what we're trying to calculate, 2 to the n. This algorithm is split into 2 steps. In the first step, it's going to break down that power n, and then in the second step, it's going to build back up to 2 to the n. So in the first step, a few things can happen. If our input n is 0, we go ahead and skip right to the second step. That's our stop condition, basically. Otherwise, if n is positive and even, we divide it by 2, and then we're going to write down an a to save some information for later. If n is odd, we're going to subtract 1 and write down a b. And then we'll continue that process until we reach 0. Now we're going to take that list of a's and b's that we have and move backwards through them. We'll start with a 1. Then for every b that we had, we'll multiply the number by 2. And for every a, we'll square that number. This might be clearer with an example. Let's look at one. So here is what happens when n equals 7. I'm going to start with 7 here. 7 is odd, so we subtract 1 to get 6. And then we write down a b. 6 is even. We divide by 2 to get 3 and write down an a. 3 is odd, so we subtract 1 to get 2, write down a b. We divide 2 by 2, write down an a, subtract 1 from 1, and we're at 0. So now, looking right to left, our list of letters is B, A, B, A, B. And we'll use those to build back up to our desired power of 2. So we start with a 1, then we had a B, so we multiply by 2 to get 2. Next we had an A, so we square 2 to get 4. We had a B, so we multiply 4 by 2 to get 8. We had an A, so we square 8 to get 64. And finally we had a B, so we multiply 64 by 2 to get 128, which is indeed 2 to the 7th. Okay, so that worked. But now we need to prove that this algorithm is complete, correct, and finite. Let's start with correct. Why does this work? Well, like I said earlier, the algorithm breaks down the exponent and then builds the power of 2 back up. When we're breaking down the exponent, we're doing 2 things. We're halving the exponent, and we're subtracting 1 from it. When we build up, we're going to do those things in reverse. So let's look at halving the exponent first. For every time that we halved the exponent earlier, when we build back up, we square our number. Undoing the halving of the exponent would be multiplying the exponent by 2, which is the same as squaring our number. For every subtraction of 1 that we did when we were breaking down the exponent, now we multiply by 2. Undoing the subtraction would be like adding 1 to the exponent, which is indeed multiplying our number by 2. So that's why at the end we'll end up with 2 to the n. Is we broke down n into this series of subtractions and multiplications, and then when we redo them to the power of 2, not just the exponent. Now let's look at completeness. Does this work for all inputs? Well, our possible inputs are non-negative integers. So we're going to look step by step. So in step 1, we have cases for 0, positive even numbers, and odd numbers. This covers all the possible inputs with no overlap. We always know exactly what to do. In the second step, we have an initial value, which is good because it means we get an answer even if we didn't have to do anything in the first step, which would be the case if our input had been 0. And then we have cases for halving and subtracting, which were the only things we could have done in step 1. So again, we always know exactly what to do, and the algorithm is complete. Finally, we need to show that it terminates, that it's finite. To show that the algorithm ends, we actually only need to look at step 1, because step 2 is going to have pieces that correspond to every operation in step 1. So if step 1 is finite, so is step 2. So in step 1, we start with a non-negative integer. If it's 0, we stop, we're done. If it's positive and even, we divide by 2. This is always going to give us another smaller positive integer, right? It can't give us something negative, it can't give us 0, it can't give us something that's not an integer. If our non-negative integer is odd, we subtract 1. This either gives us 0, in which case we'll circle back to our stop case, or it gives us another smaller positive integer. So in each of these steps, either we're stopping or getting a smaller positive integer. There are only finitely many non-negative integers less than our input, our original input. So we're only going to end up taking finitely many steps. So the algorithm must end. So we're done. We're done. We successfully showed that the algorithm was correct, complete, and finite.